The principle of a potential divider. Right before us we are having a circuit diagram, and this circuit diagram has a source of EMF, which is a cell, and it is connected to a slide wire AB. Now this slide wire AB has its length L, and we are going to get ourselves also interested in a portion of that slide wire which we have called AP, and that portion of that slide wire we are calling it length X. Now let's go on and find the potential difference across this slide wire. Now the potential difference, definitely this is a circuit now, the potential difference across this slide wire. So the potential difference across that slide wire VAB is definitely going to be given by V is equal to the current that is going through that slide wire times the resistance of that very slide wire. The same will be if we want to find the potential difference across the portion of that slide wire AP. It means that it's going to be still V, which is the potential difference across that portion of AP, going to be equal to the current that is going through that portion times the resistance from A to P. Now, speaking of the resistance of this slide wire, we are going to use our formula for resistivity. We all know that resistance can be expressed as the resistivity of this wire divided by the length of the wire over cross-sectional area. A is the cross-sectional area, L is the length of the wire, and this is the resistivity of the wire. If we are to use this value of this resistivity to substitute it right there, this is how things will turn out to be. That if you are to get the potential difference across wire AB, it's going to be equal to the current that is going through that wire times the resistance of AB. But now the resistance of AB can be expressed in terms of the resistivity of that wire AB times the length, which is the value of L, over the cross-sectional area A of that wire. So if we come and substitute this thing right there in RAB, we substitute it there, our VAB is going to turn out to be like this. VAB is equal to I, which is that current, times RAB. RAB is this expression we got, which is that right there. So we are going to get the same thing and get the potential difference across AP, which is right here. PD across AP is going to be equal to current going through AP times the resistance of that portion of the wire AP. Again, we know that RAP is equal to the resistivity of this same wire times X over A. Now X is the length of that portion of the wire times the cross-sectional area of that wire, which is the same as before. We are dealing with the same wire. So it means that therefore the voltage or the potential difference across that portion of the wire AP is going to be the current times RAP, RAP being that expression that we are substituting there, that constitutes our second equation. So what is going to happen here now? We want to compare the potential difference across AB and the potential difference across AP. When we compare them, it means we are just going to divide this, divide by that, these two equations. We shall divide them and we will end up with our expression. So when we divide VAP is equal to I times that, divide that by VAB is equal to I times resistivity times L over A. When we divide those two, you will find that the current is the same. It's the same amount of current that is produced by this. So it means I and I are the same, so they will cancel out. We are dealing with the same wire, so it has the same resistivity. So it means these two will also cancel out with that. And then this will become VAP over the potential difference across AB is equal to X over A. Divide that by L over A. Of course, this is going to end up being VAP over VAB, giving us X over A times the reciprocal of this being A over L. This A and that A will cancel. VAP will over VAB is going to be equal to, this will be giving us X over L. This is X over L. Now, if we are interested in finding the potential difference across the portion of this wire, which so happens to be VAP, that means we shall make VAP the subject of the formula. VAP is going to be equal to X over L, multiply that by VAB. Now, if you look at this expression, we find that X is the small portion, divide that by the length of the whole wire. So meaning that this X over L in essence is trying to represent the fraction of that, of the X, this AP is the fraction of the whole wire. So it is the fraction of the wire we are talking about, multiply that by the potential difference across the entire wire, which so happens to be the EMF of that wire, VAB. So this expression shows us that the potential difference across a section of the wire is always proportional to the length of that wire. In other words, if the potential difference across this whole wire is 10 volts and this wire is 10 centimeters, it would mean that each centimeter of that wire is 1 volt. That's what we mean by saying that the potential difference across the section of the wire is directly proportional to the length of the wire. This also simply means that the longer the wire, the higher the potential difference across the portion of the wire that we have chosen. Now, this principle is what we are calling the principle of the potential divider, and this principle of the potential divider is exactly what we shall be employing when we are dealing with potentiometer circuits. In this video, I get to introduce potential dividers. But what exactly is a potential divider? Now, a potential divider is a simple circuit, and it is meant to supply a variable potential difference, and it is normally used in audio and volume controls and various other applications. Now, in this video, I'll seek to explain the basics that are behind this the potential divider. But before we get into those basics, you're seeing a cylindrical shape. I'll call this a conductor. I've drawn here a conductor. And as you can see, this conductor has what we call, it has a cross-sectional area and it has a length. Now, from one of our previous videos, we said that all conductors have got a certain degree of resistance to flow of current. So if we are to look at this conductor, it is having a resistance to flow of current, which we shall call resistance, but this resistance is dependent on certain factors. There are actually 4 factors that affect resistance. Now, of the 4 factors that affect resistance, I would like to pull our attention to one of those factors called the length of the conductor. We explained earlier that the length of the conductor is directly proportional to the resistance of a conductor. And that is basically because the longer the conductor, the more the collisions between the electrons that are flowing through the conductor and the atoms, and so that definitely increases the resistance of the conductor. So in short, we need to remember that the resistance of this conductor is directly proportional to the length, meaning that the longer the conductor, the higher the resistance of that conductor. Now let's put this very conductor into a circuit. If we are to put this very conductor into a circuit like this, as you can see, we are having a cell right there, which is having an EMF of 12 volts, and we have connected it to this conductor. It means that as current is flowing out of this cell coming through this conductor is going to experience a potential difference across it as current flows through it. So this means that if the EMF of this cell is 12 volts, it means that the potential drop across this conductor is also 12 volts. That is on condition that the internal resistance of this cell is negligible. Now let's take a case in point. What if we disconnected this end of the conductor and we made this thing a sliding jockey? this wire, we put it around here like a sliding jockey, and we were able to slide it along this conductor, what happens? Now, of course, before we get to that, we know that as this current is flowing through, it is going to flow through that whole conductor back there. But if we are to connect it like that in such a way that now this becomes a sliding jockey in a way that this wire slides along this conductor, it means that as current is flowing out of this cell, it will come like that. And because this portion of the wire is at that point, it means that current will just flow through just a portion of that wire. Current won't go through up to this very end. Now this part of the conductor becomes redundant. It means that as current is flowing, it will flow into the conductor and it will just continue through like that. So meaning that if I extended this right there, it means that the current coming in will only go through there like that, and it means that this portion of the conductor will become redundant. So now what does that mean? It means that as you are adjusting this jockey along this wire, it means that you are varying the effective resistance within this whole circuit. Why is that so? If the resistance of this whole conductor is 10 ohms, it means that originally current is going to experience a resistance of 10 ohms as it's flowing through back here. The effective resistance in this circuit, in other words, would be 10 ohms. But if we are to make this current not to go through this entire conductor, and we connect it in such a way that current flows and it goes through just a portion of that conductor, it means that the amount of resistance, the effective resistance in this circuit, is also going to reduce, because as current is flowing through, it's not experiencing the entire resistance of 10 ohms. Remember, when I was introducing this, we said that the resistance of a conductor is directly proportional to the length. So it means that if this is 10 centimeters and it is having 10 ohms across this entire length, it means that if we are to bring this jockey or to this wire and we connect it in the middle in such a way that here is 5 centimeters and this end is also 5 centimeters, it means that when current is flowing through this conductor, it's going to only flow through halfway the whole thing, halfway the entire conductor. And since resistance is directly proportional to the length, it simply means that if these 10 centimeters were corresponding to 10 ohms, it means that the 5 centimeters will correspond to 5 ohms. And so it will mean that if we want to find the amount of current that is flowing through the conductor, it would mean that the amount of current is only flowing through 5 ohms. It means that this 5 centimeters is only corresponding to 5 ohms of the resistance. So the effective resistance in this circuit becomes 5 ohms, and this part of the conductor becomes redundant. So I would like to bring to your attention the fact that as we are varying this jockey along this wire, that the resistance of this wire will be varying also depending on the length of the entire conductor. Let's consider a conductor here. This conductor has 10 ohms, and this 10 ohm conductor is connected into a circuit whose EMF is 12 volts. So this 12 volt source of EMF is releasing current in that direction, and this current is going through this whole conductor and back right there. And now we are being required to find the output voltage that is just across halfway the length of the entire conductor. Now, according to the question, we are being told that the conductor is having 10 ohms. If the conductor is having 10 ohms, it means that if we are being required to find the output voltage across halfway the section of the whole conductor, it means that halfway means that it's going to be 5 ohms from here to there. This portion is 5 ohms, and this remaining portion is also 5 ohms. Where are we getting that from? We are getting that from the very fact that resistance of the conductor is directly proportional to the length of the conductor. If we are to find the output voltage, we are going to first find the current that is going through the conductor. So let me call it IS, the current going through the conductor. Let me call it the source current. IS is going to be equal to V, which is 12, divide that by R. the effective resistance in the whole circuit, and in this case it is 10 ohms, the effective resistance in the whole circuit. So it's going to be 12 over 10, and we'll find that the current flowing through this whole thing is 1.2 amperes. So now, after finding the current flowing through, it means that we know the amount of current going through. It's 1.2. So now, how do we find the output voltage? We are going to use still Ohm's law. Output voltage V0 is going to be the current that is going through. Remember, the amount of voltage, or the PD, across this section of the wire is going to be the same as the PD across this output. Whatever we connect here, the potential difference is the same across these two. So it means that it's going to be the current going through here, which so happens to be the source current. Multiply that by the resistance. In this case, since we are interested in the potential difference across just that section, it means that the resistance is 5 we are looking at. So it means that the output there is going to be IS, which is 1.2, multiply that by 5. And in this case, our output voltage is going to be, now if you look at this, our output voltage is 6 when we tapped halfway the wire, because it's 5 volts. Now this simply shows that actually that the total EMF in this whole circuit is 12 volts. When we tap halfway, it is simply going to be 12 divided by 2, because this is 5 volts, 5 volts. So it means that if we are saying that the total potential difference in the whole circuit, or the total EMF, is supposed to be distributed amongst the resistors in the circuit, and we are having this resistor of 5 ohms and that resistor of 5 ohms, since these two are identical, if it is 12, it means that this will take 6 volts across here, and this will also be having a potential drop, or a potential difference across it, of 6 volts. That's how we get 6 volts. In general terms, we shall say that if we're having current IS that is flowing out of a source of EMF, the source of EMF is what we are calling VS, and this is being connected to a conductor whose length is known, or maybe whose entire resistance is known. In this case, we are calling the resistance of this conductor, we shall call it RW, RW meaning the resistance of the wire, and we are being required to find the output voltage across a section of the whole wire. It could be halfway, it could be quarter way, or any distance across the section of the whole wire. The procedure in general terms would be that first we will have to find the current flowing through this. The current here is going to be, from Ohm's law, is going to be the EMF V, which is that over the effective resistance in the whole circuit. And now in this case, the effective resistance in the whole circuit is RW, because we only have this in the whole circuit. So after finding the current, then we can go ahead and find the potential difference across the section that they are requiring. Still using V is equal to IR, we know that the output voltage at this point is going to be the current going through that portion, which so happens to be the IS that is being produced. Multiply that by the resistance across that portion, and in this case, that it's going to be equal to the current IS is VS over RW, which is this. Multiply that by the resistance of this portion. Now in this case, we are saying this is halfway the whole wire. If the length is halfway, it means that if the resistance was RW, the resistance of that output portion will still be a half of the whole thing. Of course, if it is a quarter, it will be a quarter of the whole resistance, and so forth. So of course, when you multiply this, you'll find that we shall be getting an expression that the output voltage is going to be equal to the source voltage divided by 2. Looking at how we deal with this output voltage when the resistors are fixed, you see now this kind of arrangement is just the same as before, only that here we are dealing with fixed resistances. If you look at this diagram, it's like drawing this thing like this. Drawing it like this in such a way that here we are having one conductor, and the whole of it's having a total resistance of 10 ohms. Because it's having a total resistance of 10 ohms, here the resistances, let's say that this continuous conductor has been split into two resistors of 5 ohms, 5 ohms. And now we are being required to find the output voltage where there is the 5 ohm resistor. Still, we are going to follow the same procedures like before. We shall first find the current flowing throughout here, IV, and which current I, let's call it the source current. IS is going to be the total potential difference, V, which is going to be V over R. That is going to be 12. Divide that by R. Now the effective resistance in this whole circuit is, we are having two resistors in series, so it's going to be 5 plus 5, which is going to be 12 over 10, and that's going to give us 1.2 amperes. And again, just like the way we did before, if we want getting there for the output voltage, voltage in this case is going to be the current that is going through this 5 ohm resistor, since the potential difference across this 5 ohm resistor is the same as the potential difference that will be across this output terminal. So it means that the output voltage across this is going to be the current going through here, which so happens to be the source current, which is 1.2. Multiply that by the resistance, which is 5. And we will be ending up with the same answer like before. So likewise, if we are to use this case whereby we are dealing with fixed resistances, in general terms, this is how it would look like. That we are having a circuit like this with an EMF, with the source of EMF, which EMF we are calling Vs, the total potential difference in the whole circuit. It is having current going out of it, and this current goes through two resistors that are in series. They could be more than two. And in this case, we are being required to find the output voltage. What we do first, the output voltage, remember, the output voltage here is the same as the voltage across this resistor, since these two, whatever will be connected here, these two will be in parallel. So to get this output voltage means we are getting the voltage across this resistor R2. And it would mean that the first is to first get this IS, the current that is going through that resistor, which is going to be the potential difference. Divide that by the effective resistance in the whole circuit. And after getting our IS, we come out and get our V0. Our potential, V0, is going to be equal to I times R. I is the current going through this resistor, which is IS, which is this expression right there. Multiply that by R2, which is the resistor in question here. And of course, the rest is arithmetic. R2 gets right there, and Vs is put out. And we end up with that expression. We can always use this expression when we are trying to find the output voltage in scenarios like this. A cell of EMF 1.5 volts is connected to a wire of length 120 centimeters and the resistance is 4 ohms. Find the potential difference across 30 centimeters of the wire. So we are only required to find potential difference across a portion of that wire. The wire is 120 centimeters. We need to find potential difference just across 30 centimeters of this whole wire. And the condition here is that if the EMF here, this cell, whose EMF is 1.5, is having an negligible internal resistance. So let's draw the diagram of this and get started with the working. Now here we are having this cell. It's 1.5 volts. It is connected to a wire, and this wire, the length of this wire is 120 centimeters. So meaning that the length here is 120 centimeters. It's connected in that kind of circuit. And the question is requiring us to find the potential difference across 30 centimeters of the wire. So if the distance from here to here is 120, we are being required to just find the potential difference or the output voltage of the wire just 30 centimeters. But we know that this whole length is corresponding to, this whole thing has 4 ohms. So again, like before, to get this potential difference V, or the portion here, it means that we need to find the current going through that portion times the resistance of that end. So to get the output, V0 is going to be equal to I times R. By I, we are seeking to find the amount of current that is flowing through that portion, which we do not have yet, and the resistance of that portion, which we are still supposed to find. So let's first begin with the current. So the current that is going through this portion of the wire, let's call it IS. So meaning that current IS is going to be equal to V over R. V is 1.5. Divide that by the effective resistance in this whole circuit. The effective resistance is 4 ohms. The internal resistance here is negligible, so we only have 4 ohms. So it's 1.5 divided by 4, and 1.5 divided by 4 is going to give us 0.375 amperes. So it means that the amount of current flowing through here is 0.5 amperes. So now what about the resistance of that portion of the wire? Because we are required to find the potential difference across that portion of that wire. Remember, earlier again I said that since we do not have, remember again earlier we said that since remember earlier I said that voltage, I said that resistance is directly proportional to the length. Now the length of this whole thing is 120 centimeters, and we only need a portion of it, which is 30 centimeters. We have the resistance of the entire length, which is 4 ohms, but we do not know the resistance of that portion. So let's try and find the resistance of this portion. Since we know that R, or the resistance of the wire, is directly proportional to the length of the whole wire, we can find the corresponding resistance of that portion of the wire, so that we are able to put it right there, because it's what we are interested in. So to find the corresponding resistance of that portion of the wire, we shall say that 120 centimeters is equivalent to 4 ohms. So what about these 30 centimeters? What resistance will it be corresponding to? Let's call it X, and we find the value of X. When we cross multiply, we shall end up with X being X times that is 120. X is going to be this times that, which is 30 times 4. Divide by 120, divide by 120. And we shall end up with 30 over 120. This is actually the fraction of the wire times the total length. We shall find that this portion of the wire is just 1 ohm. So here we have the current going through that portion of the wire, which is 0.375 amperes, and we also have the resistance of that portion of the wire, which we have found to be 4 ohms. Now we can go ahead and find the output voltage of this portion of the wire, which is the current, which this times R, which is 1, which is 0.375 volts. And that's the answer. So now we're going to repeat this question. Part B is telling us that find the PD across the 30 centimeter of the wire if it has 1 ohm as internal resistance of the cell. So the internal resistance here is 1 ohm. That's a slight change in the question. So if I may redraw this circuit diagram, it's still going to be this. Now this time around, this cell, they are telling us it has 1 ohm internal resistance. So it's having an internal resistance here of 1 ohm. This whole thing is the cell. So again, just like before, to get the output voltage V0, for us to get the output voltage, we know we need to find the current that is going through this portion of the wire. The 30 centimeter portion of the wire, we already found out that it is 1 ohm. So this is 1 ohm, the rest of this is 3 ohms, this portion of the wire. So this is 1 ohm, yeah. And now we need to find the current times the effective resistance. Times the resistance, which is 1. Now we need to first find the current. Let's do some work here. The current, which so happens to be the source current here, is going to be equal to the potential difference V divided that by the effective resistance in the whole circuit, which is going to be capital R. Now this so happens to be the effective, the V here, this thing is 1.5 volts, according to our question. So the EMF, or the potential difference, 1.5, divide that by the effective resistance in the whole circuit. Now in the circuit we are having this resistance, which is 4 ohms of the whole thing of this. But remember that our cell is having an internal resistance of 1 ohm. So it means we treat this internal resistance as though it is a resistor that is in series with the rest of this. So it means that our effective resistance in the whole circuit is going to be this entire 4 ohms, add it to that 1 ohm resistor. So it's going to become 1.5, divide that by 5, and definitely 1.5, we'll end up with 0.3 amperes. So now that we know that the amount of current going through here is 0.3 amperes, it means that the output voltage therefore is going to be 0.3 amperes multiplied by that resistance, which is 1, and it is going to give us 0.3 volts. So that is the output voltage, or the voltage across the portion, or the PD across the 30 centimeter portion of the wire. And that answers our question. Now, of course, if you may want to use the formulas that we derived earlier in our general terms, or in the general sense, this would mean, now if I am to use this formula, in this case, it would mean that I'm going to say V0, output voltage, is going to be R2 over R1 plus R2. Now our R2 in this case is the resistor that is across the output voltage that we want. So in this case, the resistors that is across the output voltage that we want is 1. Divide that by the effective resistance in the whole circuit. Now in this case, the effective resistance in the whole circuit is going to be this resistor here, which is 1, plus 3, plus that other resistor, which is 1. And then we multiply that by Vs, and Vs is the source voltage. And in this question, our source voltage is 1.5 times 1.5. And definitely we shall be able, when we compute that, we still get the same answer of 0.3 volts. Again, if we were to use this approach in our first question, it would still be the same approach, only that this time around, our value of R2, it's still going to be 1 over R1 plus R2. Now in our first instance, remember, this 1 ohm was not included. It was not part of the deal. So it means that in our calculation, in the first instance, this 1 would be excluded, and would continue doing our question like before, and would still get our answer. In our previous videos, we've been looking at the unloaded potential divider. And when we're looking at the unloaded potential divider, this is exactly how it looks like. We are having a source of EMF, a cell which is having like 12 volts, and this 12 volts is being distributed amidst these two resistors. Since these ones are identical, these 12 volts with a negligible internal resistance means that it's having 6 volts here and 6 volts there. And the output voltage, the one that was required, or the one that is required, does not have any load on it. Now, that is as of what we've been doing previously. Now, when we are talking about a loaded potential divider, we are talking of one whereby when we are the portion where we are requiring the voltage output, there is a load. Looking at that illustration, for example, we are having a diagram, a circuit diagram, just similar to one before, but the output voltage, or the portion where we're being told to find the output voltage, there is a load. So we are having a load of 5 ohms that is connected to this portion of the circuit, and so this qualifies it to be a loaded potential divider. So in this circuit diagram, we are going to find the voltage output at this terminal. The procedures will be like we've been doing before. We are going to first have to find the current that is going through that is being produced here. So, and then of course we know that the potential difference across that resistor is the same as the potential difference across that resistor, and definitely it is the potential difference at the output terminals right there. So if we may start to find the amount of current that is flowing through this entire circuit, it means that the current flowing, let's call it IS, the current flowing from the source is going to be equal to the potential difference, which is V over the effective resistance R. Now, of course, the V, which is the EMF V, which is 12, divide that by the effective resistance in the whole circuit. Now, to find the effective resistance in the whole circuit, we have this combination and then that combination. So this is a parallel combination, then this parallel combination is in series with this. So to find the effective resistance means we're going to first find the effective resistance across the parallel combination, and in this case the resistance there across here, it's going to be times 5 over 5 plus 5, which is going to be 25 over 10, giving us 2.5 ohms. So it means that the effective resistance across that combination is 2.5 ohms. So if the effective resistance across this combination is 2.5 ohms, it means our diagram can be remodeled to look like this. So this is the 2.5 ohms we're talking about, the effective resistance across that combination. Now this effective resistance is in series with that resistor. So it means that the effective resistance in this circuit, if we continue with our calculation, would mean that the effective resistance will be 2.5 ohms plus 5 ohms, giving us 7.5 ohms. So 7.5 ohms is the effective resistance in this whole circuit. So to go ahead and find our current flowing is going to be equal to V over the effective resistance. Our V is 12, divide that by the effective resistance, which is 7.5, and therefore the current that is flowing through this circuit is 1.6 amperes. So we have 1.6 amperes being produced here. So meaning, to go ahead and find the voltage output right there, we shall say that the voltage output is going to be the current flowing through this times R. In this case, the current flowing is what we got here as 1.6. Multiply that by the effective resistance across that combination, which is 2.5, and definitely our answer there is 4 volts. So 4 volts is the output voltage at these terminals. Now, in the just concluded worked example, we've been using resistors of fixed resistances. However, we can introduce a slide wire. With a slide wire, it means that the voltage output can always be regulated by sliding the wire across the length. So meaning that if we get this wire and slide it across here, this is a potential divider, it is having 10 ohms. And when we slide this wire across here, it means we are regulating the resistance of this. If this is our cell, for example, we know that current is flowing in that direction, and if that slide wire is, let's say, if this is halfway and this portion is halfway, it means that current will come and only flow like that, leaving this other part redundant. So meaning that if this thing is 10 ohms, if this slide wire is halfway, it means this is 5 ohms and that is 5 ohms. And if we are to remodel this or to redraw this circuit, it would mean that current is flowing out, and since this thing is at the center and it's only going through 5 ohms, so this is like, it's like drawing it like this, that current is going through the 5 ohm resistor and this other part is redundant. Now this is what we've been doing previously when we're dealing with unloaded potential dividers. Now it's going to be the same case even when we are dealing with loaded potential dividers. Right there we are having a potential, a slide wire, and we have decided to put this in the middle of this slide wire. Let's say this slide wire has 10 ohms as its total resistance for the entire length. So meaning that if we put that wire there in the middle, this would mean that this is 5 ohms and this is also 5 ohms, because the whole of this thing is 10 ohms. So as current is flowing through, coming through the whole slide wire, and then we decide to put some wires there to tap it off, and probably we load it. We put a load here, let's say 5 ohms still. It would mean this remodeling this diagram is the same as drawing it like this, and here we're having 5 ohms, then the other 5 ohms is right there, and that is 5 ohms. Now in most cases we remodel the diagram or we redraw it for easy understanding, and we normally do this when we are at the beginning stages, but of course as you get used to these kinds of diagrams, it's not necessary to remodel it like this. It's always obvious. You just go on straight forward with the calculation. So for this case, we will do a worked example to illustrate this further. A battery of EMF 15 volts is connected across a potential divider. This is the potential divider they're talking about, of resistors 600 ohms. So these are the 600 ohms of the potential divider, I'll call it the slide wire. A load of 100 ohms is connected across the terminal of the potential. So this is the load they're talking about, and it is connected across the terminal of this. Of course, this wire can be slid along that to regulate the resistance. So a load of 100 ohms is connected across the terminal of the potential divider as shown. If the slider is halfway the divider, find the PD across the load. Now, of course, if this slider is halfway this divider, and this whole thing is 600 ohms. If it is halfway, it means that this portion is 300 ohms, and this other portion is also 300 ohms. This is coming from the fact that the resistance of a conductor is directly proportional to the length. The longer the length, the higher the resistance. The shorter the length, the smaller the resistance. So still, if we are to remodel this diagram to draw it again so that it makes more sense for some of us that are just looking at this for the first time, this is how it would look like. It would look like this. We're having the 15 ohms right there. This is the 16 ohms, but since the slide wire is in the middle, so this portion is 300 ohms right there, and then this other is also 300 ohms. Then we have 100 ohms, which is the load that is put across, that is in parallel with this, which is right here. We have 300 right there, and then 100 ohm load right there. So in this question, we are being told to find the PD across the load. So we are supposed to find the PD across the load. Of course, finding the PD across the load, again, we need to first find the current that is coming through from here, going through. And of course, finding the current means current is going to be equal to voltage over the effective resistance in the whole circuit. Now the total voltage in the whole circuit so happens to be 15 volts. Divide that by the effective resistance in the whole circuit. Now the effective resistance in the whole circuit is a combination of this and that. Now to first find the effective resistance, let's get the effective resistance of this parallel combination. We know that the resistance of that parallel combination is going to be 300 times 100. Divide that by 300 plus 100. That's going to give us, divide that by 400. So we have 300 over 4 ohms. And this is the effective resistance across that combination. So meaning that if we are to, since we have the effective resistance across that combination, we remodel our diagram, and it looks like this now. So this parallel combination has been fused into one big resistor, which is 300 over 4. And so this now is in series with that one. So we go ahead and find the effective resistance further by adding those two resistors. So it means the effective resistance R is going to be equal to 300 plus 300 over 4. And definitely there we will end up with. Now that we have the effective resistance in the circuit, we can go ahead and find the current flowing through the circuit. From V is equal to IR, we know that I is equal to V over R. That's going to be the V, which is 15, divide that by the effective resistance, which is 375, and we shall end up with the amount of current flowing through the circuit being 0.04 amperes. So it is 0.04 amperes. So now that we have 0.04 amperes as the current, so we can go ahead and find the output voltage right there. The output voltage will be V0 is going to be equal to I times R, which is going to be the current, which we got there as 0.04, multiply that by the resistance across the potential difference, across the load, which is 300 over 4. and we will end up with
Potential divider is simply a device that is used to provide a known fraction of a given potential difference. For example, in our two illustrations here, we have this kind of potential divider that we are going to call the fixed potential divider because it has fixed resistances, and so it will give out an output voltage that is fixed. Then we have a variable potential divider. This is the input voltage here, V0, and this is the fraction of this voltage that is being delivered at the end. So a potential divider is basically used to provide known fraction of a given potential difference. For example, if one which is too large to measure easily. So looking at these two potential dividers, we are going to find out the amount of current that is going to go through them. After getting the amount of current that is going to go through these potential dividers, then we are able to establish how exactly we get these output voltages. So now if you look at this output voltage V0, because this is the input voltage. Input voltage V0 is going to be equal to the voltage across this resistor plus the voltage across that resistor. So voltage here is going to be equal to the voltage across resistor 1 plus the voltage across resistor 2. So V0, which is the input voltage, is going to be equal to the current. It's going to be the same current going through this whole resistors and coming like that. So it's going to be current times R1 plus I times R2. So this is going to become I into R1 plus R2 is going to be V0. So it means that if we make I the subject of the formula, the amount of current that is flowing through, that resistor or that circuit is going to be I is equal to V0 over R1 plus R2. So now, having gotten the current that flows through this whole circuit, then now how do we get this output voltage V1? The voltage that is across that resistor, because we are interested in the output voltage, since that is the function of the potential divider, to give a known fraction of a given potential difference. And the given potential difference here is this input voltage. This is the fraction that is given out. So how do we get V1? This is current. So V1 is simply going to be current I times the resistance, which is R1. So that's going to be equal to V1 is going to be the current times R1. So we got the current as this. So it's going to be V0 over R1 plus R2, multiply that by R1. So we're going to end up with an expression like this, that R1 over R1 plus R2, multiply that by V0. I've put the R1 here and the V0 there, times V0. And that is going to be the expression that we shall be using when we want to find the output voltage in any potential divider. Find the potential difference across the output of the unloaded potential divider below when the slider is halfway the divider. So the resistance of the divider is 8,000 ohms. This is the divider, the potential divider, and its resistance here, the resistance of that thing is 8,000 ohms. It is 8,000 ohms. This is the output terminal of the potential divider. It is having an input voltage of 100 volts, and they're asking us to find the potential difference across this. Now, there are two cases. The first case is when the output here is unloaded. It means that there is no resistor at the output terminal, and this is the first case we are going to handle. In our next example, we shall be dealing with the second case where the potential divider is loaded with the resistor here, and we shall see how we get the output voltage when the output terminal is loaded with the resistor. So for the first case, when it is unloaded like that, they're telling us that the slider is halfway up the divider. This is the slider. If this whole thing is 8,000 ohms and the slider is halfway up, it means that this will be, if the whole thing is 8,000, so this will be 4,000. The resistance from here to halfway is 4,000, and the resistance of the upper part is also 4,000. So it means that R1 will be 4,000 and R2 will be also 4,000. So now for us to find the voltage output here, let's call it voltage output. So the output voltage will be equal to that R1, let's call this R1 and R2. So it will be R1 from our formula here that we had already derived. So it's going to be that resistor here, divide that by the total resistance here, multiplied by the voltage input. So it's going to be R1 over R1 plus R2, multiply that by the voltage input. So R1 is 4,000 ohms over 4,000 plus 4,000, which is 8,000, multiply that by 100, and we shall get our answer as 50 volts. Now 50 volts, that's going to be our answer. That's the voltage output for a potential divider that is unloaded. Now let's look at a case whereby the potential divider is loaded. We are having this question. If the divider below is loaded with 400 ohms at the output, so we're having here 4,000 ohms. This is a resistor with 4,000 ohms at the output, and the resistance of the divider is 8,000, so this whole thing is still 8,000. Find the PD across the load when the slider is 1/4 up the divider. If the slider is 1/4 way up the divider, it means that 1/4 of 8,000 gives this bottom part between this and the divider. So this bottom part has a resistance of 2,000, and this upper part has got the remaining bit, which is 6. So meaning that 6,000 plus 2,000, making it 8,000 volts. It also has an input voltage of 100 volts. So it means that here our R1 is 2,000. Our R2 is 6,000. So now, for us to get the voltage output, the voltage across here, we remember this is loaded with another voltage, with another resistor of 4,000 ohms. So we need to first find the effective resistance here, so that when we get the effective resistance here, then we can apply the other. So the effective resistance across the 4,000 and the 2,000 here, so we shall get the effective resistance, we shall call it the effective resistance 1 over R is going to be equal to 1 over 4,000 plus 1 over 2,000. And when we add this up, our effective resistance across this combination is going to become 4,000 over 3 ohms. That is our effective resistance across the output terminal. So it means that after getting our effective resistance here, it means that our divider has now become like this. Our potential divider has become like this. The effective resistance here, which is 4,000 over 3, has now become this, and now this upper part is 6,000 volts. Now we get the voltage output there, like that. So we apply our equation that we had derived before, that it's going to be this resistor, divide that by this plus that, times the input voltage. So to get this voltage output is going to be equal to that 4,000 over 3, divide that by the total, which is 4,000 over 3 plus 6,000, this whole thing multiply it by 100. And when we do that, our answer for the voltage output will be 18.18 volts. And that is how we calculate for voltage output for a potential divider that is loaded. And our previous example, we are dealing with the case where the potential divider was unloaded. This brings us to the end of this video. Thanks for watching. Somebody out there would like to watch this tutorial. Please don't forget to like and share. For more videos, please simply subscribe to this channel. Catch you in the next video.